My privilege to introduce our chair for this next session, Nina Elisto. Nina Elisto works as a senior scientist in the design and operation of energy system research at VTT, Technical Research Center of Finland. She received her her master's and PhD degree in electrical engineering at Aalto University in Finland in 2012 and 2024, respectively. Since 2021, she has been acting as a cooperating agent of the international network EIA-WIN Task 25. And please join me in welcoming Nina to lead this session. Thank you, Nina.
Thank you, Edward. So indeed, this second session will be about offshore wind integration and enhanced grid utilization. And let's again take first the presentations, or the 4 presentations, and then all the questions at the end of the session. So we will have 4 great speakers in this session from Canada and Europe. And the first speaker is Antje Orts, who works as a chief engineer for the Danish transmission system operator Energinet, with responsibilities in international infrastructure development in the European Association ENTSO-E. And in ENTSO-E, she leads the elaboration of the offshore network development plan. And Antje is also active in IEA-WIN Task 25.
Thank you, Nina, and thank you for having me here. I assume that is too high. So, yes, I would like to inform you how we do the offshore planning in Europe, and we do it now also for the entire European system. The first edition has just been published in January this year, and I will go a bit into details how we do it. But first, let me give a bit the framework for it all. So this offshore network development plan is actually part of the 10-year network development plan, which you heard about already from Madeleine. So this is the thing which obviously also inspired the FERC order 1920, was my impression when hearing about that order last week. And here's how we do it. So we start with scenarios. Then as a second step, we assess the needs for transporting the market flows with our network. Then collect project proposals from project promoters. These can be third-party project promoters or TSOs. Not loud enough. Okay, I can also use my legs. So. Fantastic invention. Then we do cost-benefit analysis for all these projects against the same scenarios from step 1. And if a project promoter wants to have some support from the European Commission, then there is the opportunity to apply for the so-called status for project of common interest, which has then some advantages related to permitting procedures, or might also give some co-financing from the Commission. So, but the ONDP is part of this needs analysis. So this is a high-level corridor assessment. Once again, the scenarios that we do are usually, very early time it was 4 scenarios, last times it was 3. So one central scenario based on the national energy and climate plans, and then a bit to the left and to the right. For the time horizons 30, 40, and 50. So the name of this 10-year network development plan is actually misleading, as we are looking up to 2050. Then this needs analysis is about connections between countries or market zones for some countries. So it's, but we are all now discussing that the internal grid reinforcement inside a country are getting more and more important. So we might evolve in that direction, but that is still being discussed. The outcome of the needs assessment is then information on how much renewables do we integrate, what does it cost, how much. In that edition, we also focused on necessary gas import from outside Europe, read Russia, and then have the information, the costs, and compare the situation with doing nothing against various level of infrastructure expansion. Then we have this cost benefit analysis. So we have 12 benefit indicators. We have 2 cost indicators, CAPEX and OPEX, and some residual impact indicators on each and every project, which is around about 160 projects, is then assessed, giving results for these indicators against the scenarios. And this is done by calculating the European system with and without that project. And then the difference is the level of the indicator. And then we get a map. And on the internet, then you can click on these projects. The colors indicate different development status. Then you can click on the project and get all the information from the steps before. So that's the TYNDP, 10-year network development plan. So now, but speaking about the offshore plan, this was the first edition we had in January. And so it developed in parallel to the ongoing TYNDP. So it followed a different separate timeline, but now we are working on phasing it into the next process so that it will be one big calculation. So the process is it's a collaboration between member states. So the political targets, the member states have to deliver their offshore ambitions in gigawatt to the European Commission. Then we as NSOE are responsible to translate this into infrastructure needs. Then the Commission in parallel developed guidelines on how to share the costs, because the question is, it will not be the case that in the long run, only the coastal countries pay for whatever is to be built offshore, and then the landlocked countries receive the electricity, but there should be a balance on cost and benefit. But it's complicated discussion. And now we are in the phase of member states have already to deliver the targets for the next round, for the TYNDP 26. Their deadline is Christmas Eve. And while we are in NSOE in the phase of applying the recently published guidelines on how to calculate this cost sharing. So what is the ONDP? The ONDP is the translation of the political ambitions into infrastructure. So this means, where do we need to build infrastructure? How does it look like? Is everything meshed? Is it only radial? Is it a combination of both? What do we need to buy? What do we need to install? What does it cost? So it's not only one report. So it is one pan-European report, and it is one report per sea basin, meaning 5 sea basin reports, then a report about methodology and how we included stakeholders. We have a visualization platform where you can download see the results of whatever country or region you would like to see. Links are here. This is an impression on the level of capacity. This is all capacities. We took the TYNDP 22 edition, mounted the new targets for offshore on it, and then did our calculations. And you can see it is roughly the size, order of size, what we also had in the TYNDP 22 edition. So, and then these are the member state targets. We have round about 34 gigawatt installed in European waters today, including Great Britain and Norway. And then, you see the targets. And it means that we have to install 22 gigawatt each year, knowing that we needed 30 years to come to these 34 gigawatts, which we have today. So this is really ambitious. And taking Wind Europe statistics, it means that we need to be 9 times faster than we have been on average per decade, the last 10 years. So what we did is doing linear optimization. So we decided that the radial, the close to shore projects will probably be mostly radially connected. Otherwise, it would become too expensive. And then we gave the far away off the coast projects to the optimizer, so that the optimizer could find whatever neighbor to connect to. And at the very bottom, you can see very, very light green, also some projects that we know already today, which are negotiated between TSOs or member states. We did not touch them. We assumed they all will materialize. This is just a quick overview that the sea basins differ. So the big light blue chunk, this is in the northern seas. So the northern seas country really have high ambitions. Baltic Sea, 70 gigawatt, this is kind of same pace that was there before. So in the northern seas, we need to be 8 times faster. And the southern European sea basins do not count so much on offshore wind. They actually have very steep coasts and they have super opportunities for photovoltaic. So it's not necessary for them to count on offshore RES. This is how we did it. So we know actually from the maritime spatial plans that the member states have to deliver to the Commission where the spots are, where some offshore wind is planned. So we took these spots because we needed it to assess the cable length and then gave these, it's the same color code, gave this to the optimizer and then added also a bit of length, not using the bird's eye distance, but a bit more because sea basin is used by multiple users. So there's fishery, military, sand extraction, you name it. And so we have to surround things under the water with the cables, so cables get longer than you might think. This is, usual way of linear optimization, some starting grid, then inserting candidates, which is essentially from each point to everywhere, then getting the results and then making sense out of it. So plausibility check and translating this to discrete values that technically make sense. And that was then also agreed with the TSOs. And here are the results. The big dark green amount is what is connected radially. And usually in a European discussion, there's a lot of focus on these offshore hybrid projects. Offshore hybrid projects are the projects both with dual functionality, so both connecting countries or market zones and connecting offshore RES. Was just mentioned before to Great Britain. This line link is one of these. But usually then the radial connections are forgotten in these discussions, but they make most out of it and they need to be paid. They need to be produced, the assets by the manufacturers. And so Europe needs to be prepared to be able to deliver this. Also offshore vessels. There's a lot of issues that need to be solved to facilitate also the simple way of connecting offshore RES. What is new is that we invited the RGI, the Renewable Grid Initiative, to write a chapter in the Pan-European report, because when you imagine alone in the northern seas, 333 gigawatts of offshore wind to be installed in the next 20 years, this means constant noise underwater. This means something for sea mammals. And we need to think about the environment before starting. And the Renewable Grid Initiative is a collaboration of TSOs and NGOs. They know a lot about nature underwater. And so we collaborate now to find out what to do. It is, they don't have the recipes, but they know which data to collect in order to avoid mistakes in the future. So you see 2 pictures. One is a fish hotel from Tenet, where fish can put their eggs and then they get their children, and environment is harmed not as much as if these fish hotels were not there. This is also the results. You see also the sea basins and the amounts of gigawatt and how under optimistic conditions, the high-level corridors could look like. So optimistic condition means we have the cost, the prices from before Ukraine war, before inflation, to have the same price level as we had in the T1EP 22. And we assumed we do have DC breakers. Until now, nobody has installed this DC breaker in Europe yet. So, but we assumed they will be there and we will apply them. And here you see different ways of how things could evolve to the left is with this DC breaker, to the right is without. So we will have substantially less international connections in the water when the DC breaker is not there. And the price is kind of the same. So for the same amount of money, we could get very different interconnection level in the European system. And it was up to half of the amount that we have identified of international connections in the T1EP 22 for all Europe. But this was then only in the offshore basins. The cost also results in green, you see the amount only offshore for the entire European system. And in red, you see the amount that is to be spent in the Northern Seas system. So this is also something new, that we published a shopping list. The manufacturers like it a lot, and actually this has accelerated the discussion on political level, because now they know what we talk about. It's not gigawatt and something abstract, but it's kilometers of route lengths. And route lengths does not mean cable lengths, because HVDC has at least 2 poles, and meaning at least double that length, but depending on the design, it can also be more. Currently, TSOs stand in line before the doors of the manufacturers. Some have already booked next 7 years of production for cables, for example. So it's really an issue with the supply chain. Time is nearly over. So the benefits of connecting countries or market zones, you know them, I'm sure. So, and Madeleine mentioned them very nicely. So we have increased energy security, prices converge between countries, which is good for European economy. Offshore is used in a better way. We have some headaches, which is some technical issues need to be solved or found out how to do it, but we are engineers and should be able to solve these issues. I mentioned already the supply chain, but also ports are an issue. The European ports are not prepared to install this amount of offshore RES. So one figure I always remember is you need for 2 gigawatt offshore wind farm, you need 2 hectare space to assemble things for 2 years. And the harbors need to know. And there are also other industries who want to have space in the harbor. Cost sharing, there was a report published by a consultant hired by the European Commission on how this could be done. So there were questions like what to compare to, what is the counterfactual to the situation, difficult discussion. Recently, then the Commission published their guidance, but still it's a bit fuzzy here and there. And we still, when doing the translation into what actually we do to have to calculate, we still have some questions, but are in discussion with the Commission and also among ourselves with stakeholders, what actually to calculate. As this is difficult, when you want to have cost discussion between of coastal countries and landlocked countries, you have different discussions as compared to when you only are coastal countries and have the same issue. So now we TSOs from the Northern Seas and from the Baltic Seas, we have found our own organization to think how we can move on. And there we published already 2 expert papers and will come out next summer with the next expert paper, hopefully with meaningful proposals how we could do the cost sharing. And then when it works, then we can also try to convince the landlocked countries to participate if it works. Let's see. This was it. Thank you.
Thank you, Antje. And the next speaker is Stuart Muller, who leads E3's Canadian office in Calgary with a focus on growing E3's presence in asset valuation, resource planning, and climate pathway studies. Stuart's current clients include institutional investors, infrastructure funds, project developers and utilities on valuing and assessing assets, projects, and portfolios that support the clean energy transition and the reliable provision of electricity. Welcome, floor is yours.
Great. Well, let me move this up a little bit, and it's super loud. I don't know if all of the Europeans know this analogy, but I feel kind of like the little kids that play hockey in between the first and second period at an NHL game. We're up here talking about Atlantic Canada and offshore wind. We just had a great presentation on what it looks like in Europe and miles ahead of where we are today, which is really exciting for me because there's lots to learn and there's lots to take from that. But at the same time, I think we also have our own unique challenges and our own unique perspectives on this. So my talk today is going to be about Atlantic Canada and the transmission and the offshore wind associated with that. We have started and we're part of a national study for Net Zero Atlantic, which looks at the overall integration of offshore wind across PEI, Nova Scotia, New Brunswick, and Newfoundland. It's a $6 million study. We are one of a couple consultants that are supporting it. And I think, firstly, like any good consultant, we kicked off the project and now we're declaring victory and talking about it. So we just started, we're not done. The actual grid transmission piece is coming as the third part of the study and will come up. But really the goal here is to come up with kind of key outputs for developers for offshore wind, specifically around wind speed profiles, high resolution wind speed profiles, to help try and spur some of that industry. And it is very expensive. It is very challenging trying to get some people at the table. The second is to highlight some of the operational challenges and opportunities that we see in that space. And then what we can do with grid infrastructure to support it, how much that's going to cost, and kind of what hurdles we have to overcome. So all of this is going to take place over the next year and a half. It will be released once it's out. We're very excited to see the answers, but even in the first stages, in the opening kind of months, we're able to pull, I think, some interesting things out. So for those that aren't familiar with Atlantic Canada, or Canada in general, we have a very kind of bipolar energy system. We have strong goals for decarbonization at a national level. We even have strong goals for decarbonization, I would say, at most provincial levels. However, we have a number of provinces that are well on the way to decarbonization, and we have others that are challenged. When we look at Alberta, Saskatchewan, and some of the Atlantic provinces, there's a significant amount of thermal, there's a significant amount of solid fuels for thermal, and there's limited access to hydro. Now, this forecast that you see here was put out by the Canadian Energy Regulator last year, and it shows a pretty aggressive transition for Atlantic Canada. Two things in here. One, there's a lot of hydrogen production in here, and there's a lot of discussion around hydrogen production in the region, so that's driving a lot of it. But two, you can just see there's a huge amount of wind that needs to be put in place. Now, this graph doesn't break down offshore wind versus onshore wind, but clearly, or I guess not clearly, it's kind of like it is here. The solar resource isn't great. It's always a little bit cloudy. And so we're looking at a lot of wind to support that. Now, I think the most important piece, and we're going to spend some time on this slide, so I'm going to try and slow down a little bit. But when I start to look at transmission supporting offshore grid, or offshore wind, excuse me, this is the existing transmission within the Atlantic Canada region. We have 4 provinces. They all have coastlines. They all have ambitions for offshore wind. None has been built. There are transmission lines that exist between them. And I know the numbers look relatively small, but compared to the size of the jurisdiction, it's a fair amount of robust transmission. There's 2.5 million people that live across these 4 zones. So it's much, much smaller than a lot of what we talked about today, but it's still a huge potential for decarbonization in the region, and a huge potential for investment and jobs and some of the challenges or economic benefits that face some of the challenges of that region today. New Brunswick is tied in with ISO New England. We heard a lot this morning about interregional transmission and the importance of those connections, those market connections. Like, one of the realities of Canada is that we are very diverse east to west, but we have a lot of trade opportunity north to south. And the offshore wind in this space is going into ISO New England, which is one of the states that has some of the most ambitious decarbonization goals and needs the capacity more than anyone. We heard from the first session today just the value and the importance of resource adequacy or capacity as we start to think about interregional transmission. That's true no matter where you are, and I think that's true north-south here in Canada as well. What we started to find here is that while Atlantic Canada might be behind a touch on development of offshore wind and development of transmission, there are a few key components that I think actually put them or give them a leg up from where we are in the past. The first, or for where other jurisdictions are, excuse me. The first is just looking at this map, you can see the amount of interregional transmission that already exists and is used heavily for both reliability and cost reduction. This is all of these provinces here have either a publicly owned utility or an investor-owned utility. They're all vertically integrated. There is no energy market. There is no capacity market. They're all centrally planned individually. There's also no transmission planning process for all of them. Each of the owned utilities will have transmission planning internally, and then they will get together as a group and talk about interregional planning, generally with the federal government at the table to support it from both a cost perspective, but also they have an ability to convene, which is something that is extremely valuable in these circumstances. But we have a history of supporting each other, and we have a history of building this interregional transmission. You can see here, there's a proposed line on the bottom between Nova Scotia and New Brunswick. About a few years ago, there was a fairly public announcement that the Atlantic Loop was going to go ahead. The Atlantic Loop was a single transmission line that would loop all the way around these four provinces and connect them with Quebec to provide access to hydro from Quebec and also to provide a route for offshore wind into Quebec. Unfortunately, that project has been put on the back burner, but the dotted line on the bottom is one of the segments of that has been identified for reliability and reliability only. I think it's interesting, there's not a ton of interregional transmission projects that I'm aware of that have been permitted only on the reliability piece without kind of that production cost or that energy cost reduction piece. So from a first step, I think Atlantic Canada is in a very good space just from a collaboration perspective. The parties at the table are used to working together. They've already worked together. There's a lot of hope there in my mind. The second piece that we found is that there's always a lot of talk around using existing assets for supporting offshore wind development. Two ways that generally comes up. The first is looking at what coastal assets are going to be retired and how can we use those interconnection points and the headroom on that grid to support new investment. We have where the little star is here in Nova Scotia, there is a very large coal plant that is retiring, that does provide value and does sit on the coast and has interconnection assets. What we're finding though is it's a drop in the bucket. It gets a lot of airtime. We talk about it a lot, but personally, we don't see it really scaling, or it can't scale, and we don't see it of the scale that we're going to get the widespread development. The second is that when we look at grids onshore, not so much offshore, but onshore, there's a huge challenge around headroom, around interconnection, around around congestion, excuse me, and opening them up that often can have either the same or higher costs than the offshore wind cables themselves. And so what we're seeing here what we're seeing early on in our work is that it's not just the specific access to offshore platforms, not just the cables that you build, but rather the onshore grid needs to be able to support a whole bunch of energy that's coming in a very different place than where it did previously. The last point I want to make about this is really, again, came up this morning, but really about cost benefit and sharing of those items. We don't have a system in Canada, and I think they're very hard to design, obviously, but we don't have a system in Atlantic Canada specifically to allocate costs and benefits formulaically across the different participants here. And everyone's going to get a different benefit. Everyone's going to have a different cost. There's going to be different risk allocation. This is something that we see, I think, in all countries across the world. Canada is not unique with long line infrastructure, but there's going to be some very serious conversations around cost benefit sharing. Again, the size of the organization or the size of the region, I think supports, on one hand, fewer people at the table and potentially more chance of success. On the other hand, fewer people at the table, a less diverse set of needs, and as a result, a more challenging exercise in finding win-win. Often, as you add diversity to the system, you can find optimization across a whole bunch of different portfolios or a whole bunch of different constraints, where if you have just a few parties, that can become harder. So the studies now, right now, is looking at kind of the tailwinds and the headwinds, excuse me, facing Atlantic Canada's offshore wind. I think you could change the name on this slide and put it for just about all jurisdictions, which is not a surprise. I'm very gladdened to hear that some of these have been overcome in other jurisdictions. But one of the things that I think is important to note is it's important to note that being the same as others is probably a good thing. At the end of the day, we have countries in Europe, we have New York, we have California that are ahead of us on this track for offshore wind, both from a transmission perspective, but also from a technology perspective. In my opinion, maybe Atlantic Canada is not the right place to pilot new technologies. With such a small group of individuals and such a small rate base, it can be very hard and very costly to share those costs. However, being a couple of years behind gives us the opportunity to look at the planning metrics that are coming out of Europe, look at the design that's coming out of California, look at the interconnections that are being done in Maine and New York, and understand kind of from their learnings or from their first cut, what's the right way to do this for us? What's the right way in Canada to do it? Understanding that we have a different set of priorities and a different set of challenges. What's the right way for us to do it? At the same time, that also gives the supply chain time to sort itself out, to come down the learning curve. When we look at kind of solar and wind, onshore wind as an example, the original contracts in Ontario are for 80 cents a kilowatt hour. They're hugely expensive. But we've let other jurisdictions, and Ontario was one of the first, but we've let other jurisdictions bring that technology down the cost curve. I look at the cost of those DC converters that we just saw in the last presentation. Really excited for those to become commercially operable somewhere else, and be able to leverage some of that. So, from an Atlantic Canada perspective, there's a huge amount of opportunity for offshore wind. There's a huge amount of opportunity to support not just the region's decarbonization goals, but I think also markets that are adjacent to it. Quebec, I didn't mention this on the last slide, but Quebec is a hydro-dominated system with years of storage. It's one of the largest batteries in North America. Offshore wind pairs very, very nicely with that. And so as we start to look at kind of the integration across Eastern Canada, but at the same time, as we start to look at what other jurisdictions are doing and how to be cost effective and how to develop cost benefit sharing programs or practices, it's something that we can leverage. So I'm very excited to kind of be one step behind on this one. There's other things that we're one step in front. But thank you very much for your time.
Thank you, Stuart. So the third speaker is Damien Flynn, who is an associate professor in power system operation and control at University College Dublin, Ireland. And he also represents Ireland for IESVic tasks 25 and 58. The floor is yours.
Hello, good afternoon. So I'm going to talk a bit about the sort of grid enhancing technologies that were talked about earlier, and a bit about connecting between systems, but in a slightly different way. So I'm going to be focusing on the Ireland system. I guess you're probably not that familiar with the Ireland system, so I'm going to say a little bit about that and to say some of the things that have been thought about. So this is two versions of Ireland. So the figure on the left is showing the sort of the load centres. And what I'd like to highlight is that most of the load is on the east side of the country. And there's also a lot of data centres on the east side of the country. And the right-hand side figure is showing the generation. So the sort of the mustard yellow circles are the sort of the combined cycle gas turbines. And a lot of the renewables are the green circles, and they're mostly on the right-hand side of the country. So as the power system is decarbonizing, you're getting into a situation where a lot of your generation is on the west and most of your load is on the east. And then that implies that you need to build a network to actually transport the energy from where it's generated to where it's being used. And this is some figures from last year, 2023, showing the amount of wind dispatched down. So in Ireland, a distinction is made between network constraints, which are local, and system-wide constraints, which tend to be stability level issues. So you can see across the year, there's a lot of blue associated with the network constraints, and that's maybe 5% of the wind has been curtailed due to these network constraints. And then there's also a lot of system level constraints because we're looking at non-synchronous generation on the system. And if I show a similar figure based on time of day, then you can see that the network constraints are fairly constant, irrespective of the time of day, while the system stability constraints are more severe at night, which is what you would expect. There's less demand on the system, there's less thermal generation on the system, stability issues are more apparent. There is also an increasing amount of solar on the system. And from a power system perspective, wind and solar are the same. They're both non-synchronous generation. They both cause sort of system stability concerns. And you can see that there's a lot of blue here. There's a lot of network constraints associated with that solar generation. Even though there's only about a gigawatt or 1.5 gigawatts of solar on the system, it's only contributing a small amount of energy, relatively speaking. And it's because it's seen in the same way as wind on the system. So in terms of, this is sort of my interregional slide. So the Ireland system, it operates as a single power system, but it consists of two countries. So the Republic of Ireland in the south and Northern Ireland in the north. And there is a single double circuit line interconnecting the two systems. And the system actually operates essentially as two small systems because there's always that fear that this double circuit line will fail and you'll get a system split and then you'll end up with two subsystems. So there's a limit on that interregional power flow between the two subsystems. So for the last 15 years, maybe longer, there has been talk that we must have a second interconnector between the two subsystems so that we can actually operate as a single system. So there's been talk about cost-benefit analysis. It is blindingly obvious this is the right thing to do, but it hasn't happened quite yet. So partly because there are two countries, one of the challenges is that there's always an election a couple of years away. People don't like to make decisions. Once there is an election, the new government says, we need to revisit this. We need another independent plan. So there have been at least 3 or 4 independent plans saying, should we have an interconnector? And the question that always gets asked is, why don't we go underground? Why don't we have cables? And it's the same answer every time. It's a stupid answer. But it's a repeated cycle. So at the moment, I was just checking earlier, at the moment, the plan is that the second interconnector will appear in 2027, but we will wait and see. If that happens, that provides benefits for both Northern Ireland and the Republic of Ireland because it essentially means that the system can operate as a single system. It means that you can begin to push your thermal generation of the system because you're always concerned, what if you did get that system split? You need all of those standard electrical things, inertia, voltage support, inertia level. If you can operate as a single system, you can push those off. You can get higher levels of renewables in both the southern part of the system and the northern part of the system. So looking at Ireland's plans, so it has an 80% renewables target by 2030. We were hearing earlier that GB has a 100% target by 2030. The difference between the two is that GB has nuclear, so it has its Synchronous machines. Ireland does not have nuclear, and it won't have nuclear. So it's relying on wind and solar, which are non-synchronous, and it's relying on thermal generation. So it has major ambitions for lots of solar, lots of wind on the system, both onshore and offshore. So 2030, this is what we might have. So on the left-hand side, we've got the demand, lots of data centers on the eastern side, lots of electrification of heat and transport. And on the right-hand side, we have our generation map, lots of offshore wind, lots of solar appearing on the system, all wanting to connect to the grid. And 2030 isn't that far away. So as in many countries, building transmission is very difficult. It takes a long time. So alternative technologies that try to use the existing network more effectively have been, I suppose, historically the focus. Because what we want, as the picture shows there, lots of wind on the west. We want all of it to sort of, or most of it to go to the major load centers on the east. So it's about looking at technologies that can actually help us better use the network. So there's questions earlier about these grid enhancing technologies. There's a wide number of them. Dynamic line rating, also using high temperature, low side conductors, using STATCOMs, static VAR compensators, power flow controllers, using batteries, and so on. There are a wide range of measures. And the question is, which ones should we use and where should we use them and what are the most cost-effective options? I don't have time to go through all of these. I'm going to focus on a few of these, mainly dynamic line rating, but also mentioning a bit about power flow controllers and energy storage. So one of the things that we've been looking at is weather-based dynamic line rating. So whenever it's windier, you can increase the ratings of your lines, you can carry more current, and that can avoid the need to upgrade the network. So this is looking at a weather-based approach where instead of installing monitoring equipment on the lines, you can actually use your meteorological forecasts instead. So I won't go into the details of this slide, but essentially we were running an optimal power flow, combining that with unit commitment in order to make probabilistic judgments as to what were the cost-effective decisions to make. So this is looking at the line upgrading potential based on the probability of being useful. And what I should highlight is what we're also doing here is implementing seasonal line rating. So in the background, instead of the line rating being fixed, the line rating is actually varying with the season, given that the ambient temperature is changing. So whenever it says greater than 0.2 per unit, my megawatt rating for the line is actually varying with the time of year. So if you say that you can achieve a 20% increase, you can see the figure on the left. If you're more ambitious and you want a 40% increase, then the likelihood of being able to achieve that on a regular basis is obviously going to be lower. And one way of presenting this is in terms of locational marginal prices. So Ireland doesn't have locational marginal prices, but it's a nice, convenient way of emphasizing constraints in the network. So looking at the figure on the left, you can see that there's a lot of red on the right-hand side. That's where all the loads are. The network is congested. and hence you're getting high prices. On the left-hand side, you've got a lot of green. That's where your renewable generation is, and the prices are low. So if you then apply dynamic line rating, and there's a lot of purple here, which implies that the locational prices are going downwards. And you can see similar things in terms of the dispatch levels whenever you add in dynamic line rating, that you can reduce the amount of wind curtailment that you're seeing on the system. And you can see that in terms of line constraints. So I'm going to switch to something that's slightly different. I'll just say in passing, this is looking at the advantages of putting batteries in the system, because they can also help with local constraints, and power flow controllers or distributed static series compensation can also help. And the nice thing about these measures is that they're short-term solutions. You implement them, they give you a solution. Sometime in the future, you upgrade your network, and then you can move these around the system to where the network is now constrained. Some of the earlier talks have talked about system planning. In Ireland, they've sort of looked at it in a slightly different way, in that the scenarios that they've looked at have deliberately not been sensible. Maybe that's not the right word to put it, but deliberately controversial to make people think. So one of the scenarios was essentially that of a vertically integrated utility. So going back to the days where a utility owned all the generation, owned all the network, what would it do? And this is showing that the major changes are on the east side of the country, where the major load centers are. And what you'll be doing in terms of generation is that you'll be building a lot of offshore wind off the east coast of Ireland. So you'll be placing your generation close to the load, so you don't actually need to build that much network. The second approach is the traditional approach, whereby developers decide that they want to build a wind farm somewhere, they want to build a solar farm somewhere, and then it's up to the system to actually accommodate those needs. And that tends to lead to a more expensive approach. There's more projects involved. Those projects take more time to build. Another approach is sort of trying to use some of those grid enhancing technologies that I talked about earlier. So using your power flow controllers, using dynamic line rating. And what this figure is showing here is emphasizing if you used HVDC. So you can see you've got very long HVDC lines and underground cables going across the system. So a technology option, but an expensive option. And then the final option is that Ireland has a lot of data centers. So at the moment, about 18% of the load is data centers. By 2030, it might be 25 to 30%. So instead of putting the data centers near where the loads are, put them near where the generation is. So put the data centers in the west of the country. Not a solution that data centers are particularly happy with, but the idea was to look at these four very diverse solutions. And in the background, there was a large public consultation process to sort of look at these different options and what, as a country, do we want to do. In the background, people were experiencing very high electricity prices. We had the sort of recovery period of COVID. We had the war in Ukraine. Ireland was importing gas. People were seeing very high electricity prices. So the idea that if Ireland could adopt more renewables, it would be less dependent on importing gas. And if the downside of that conversation was building more transmission lines, then that would seem like a reasonable thing to do. So my final slide is that normally when there's public consultations in Ireland, there can be a lot of unhappiness about proposals. And unusually for these proposals is that there was a lot of strong public support. And I think it was fortunate in the timing that people were experiencing those very high electricity prices. And unusually, there was very low opposition groups. So I'm not saying that Ireland has solved this, and we have to wait and see if lines are actually going to be built to support all of the story of Ireland being self-sufficient in terms of energy and transmission being a cost as part of that process is perhaps a story that has been helpful. Thank you.
Thank you, Damien. And the fourth speaker is Ana Estanqueiro, who is a research scientist at the Portuguese National Laboratory for Energy and Geology, where she coordinates the scientific area of renewable generation integration in energy system analysis. And she is also an invited professor at University of Lisbon. Ana is also active in IESVic and its task 25.
Thank you, Nina, and thank you, Madeline, for the invitation and for all this audience interested in these subjects that we research so happily for a long time. I am aware that the greatest interest is on interregional transmission connection, and what I choose to present here is directly related to interregional connection, but it's mainly related to transmission of electrical energy in general. So for many years, we have been interested in Task 25 in something that some of you may be aware of, which is dynamic line rating of mainly overhead transmission lines. And more recently, interests arose in relating that capacity of rating dynamically the transmission line capacity of transmission with the potential interconnection of variable renewables, namely wind generation. And that's what we are going to address here. This presentation is based on an article that was recently submitted to a journal, and I acknowledge my co-authors in this article. And as a context for the ones that are not very aware of what is dynamic line rating, what I wanted to highlight is typically and traditionally grid operators, being transmission system operators or even distribution system operators, would rate the capacity of transmission of lines in a static form. So attributing average temperatures and other parameters and fixing the capacity of transmission of the line. Quite recently, and I'll pass this, quite recently in the past decades, we started to look at that capacity of the lines as something that we could actively calculate and change in function of mainly weather parameters. So if we look at the transmission line, we have the movement of the charges that tends to heat the line and provoke certain thermodynamic effects within the line. And if we relate that thermodynamic situation with the weather effects, mainly radiation, wind, and the environmental temperature, what we conclude is there are effects that tend to diminish the transmission capacity of the line, for instance, the ambient temperature, even the radiation, and there are other effects, weather parameters that tend to cool down the line, thus therefore increasing the transmission capacity of the line. And they are somehow represented in this first image and graphic. And one of the easy conclusions to take from this is the same wind resource that increases the charge of the line also cools the line and then increases the capacity of transmission of that line. Therefore, one of the main motivations to these studies related to grid integration of renewables is to explore that effect and what can we expect to have more in terms of capacity if we apply these methodologies. So in review, dynamic line rating was firstly defined and started to be researched in the 80s of last century. Quite recently, it was object of a more recent interest, I would say, related to the huge investments in new transmission lines. And also, I am not aware of the situation in Canada, but in Europe, also related to the great difficulty in obtaining environmental permits to build new transmission lines. So I could say is fair to say that in Europe, transmission system operators need to apply all possible methods to avoid new lines. Quite recently, in 2014, simplified approaches appeared. Those simplified approaches are not as powerful as the full dynamic load concept, but they are simpler to apply in practical terms. In general, what we could classify the application of this research is on the reliability of the lines, on the management of congestion, especially for pre-identified situations, and also on the estimation of rating on an operational basis, so based on the forecasting of the weather conditions and the rating of that line. I have collected with my co-authors the experiences gained in the IEA Task 25 countries, and I report this experience here, starting with Germany, where they are conducting several pilot projects and monitoring the line capacities. I should say that these applications of dynamic line rating, typically they monitor the temperature of the line. Some of them also measure the wind speed direction and average in specific critical points of the line. And they apply these experimental data together with both weather forecast systems and also the forecast of the load flow in those lines. So there's also an operational perspective in the application of these concepts. In Portugal, we can report that is a rather classical situation. So most TSOs do not apply the dynamic rating as it could be or to the full potential. What they apply is a static rating, and the most advanced ones, what they do is to recalculate that static rating, for instance, on a monthly basis or even on a seasonal basis. I wouldn't talk too much about Sweden, especially because Sweden reports a bad experience with the DLR. But in the United Kingdom, they applied this concept for the distribution network. And again, they obtained quite good results. United States is one of the countries that is exploring in greater detail the possibilities of dynamic light rating, especially because an overview study that DOE prepared concluded that different independent operators were classifying the rating of the same line in different ways. So there was an order issued in 2021 that gave those operators 3 years to apply new methodologies that, although are not the most powerful ones, at least they are easy to implement and guarantee systematic application of those procedures. So giving some examples, this is a study that we did quite recently, and we did this study to assess what would be the capacity of 2 zones in Portugal, each of those zones characterized by an abundant resource of a renewable technology or primary source. The one on the top, more on the north, is what we called a windy area. And what we could conclude is there was the possibility to interconnect something like 2 gigawatts of extra wind in different points of that grid without further reinforcements of the grid, just by using the extra the extra capacity that was generated by dynamic rating of the lines. Of course, this implies that some control needs to be installed in the wind power plants, because for certain precise conditions, we may not have enough capacity to transmit all the generated power. One of the, if we look at the bottom image, it is a situation of a region of Portugal where the solar resource is extremely high. And what this graphic tells us is almost for 100% of the time, we have a very large extra capacity in the lines if we want to use it. This is an example of the United States. This is an experimental example. So they applied the numerical tools, but they also did measurements in those lines. And if you look here, we have 5 lines, and for 4 of them, they can operate the lines with extra dynamic capacity. And for a single one, they can do it for 80% of the time. Other possible applications, I give an example of Portugal. This is directly related with the inter-regional connection, because we operate the Iberian Peninsula as a single electricity market. And one of the things that has more impact on the operation of that market is when the interconnection lines between the 2 countries are congested, and the markets, we call them, are split. So they need to be operated in a separate form. So we apply to the interconnection lines, we simulate the application of DLR methodologies, and we concluded that the periods, the annual periods for one typical year, 2018, of market splitting would reduce from 456 hours to only 186 hours. This would mean, in terms of the conversion of costs, that they would reduce from a difference of 8.89 euros per megawatt hour to 6.12 euros per megawatt hour. So the impact is meaningful for this situation. This is an example of the United Kingdom. And again, in the same situation, they use a methodology that is very similar to the one that we also applied in Portugal, with the identification of critical points that limit the capacity of the grid. And in terms, is a simpler graphic, but in terms of the comparison with of the dynamic capability obtained with our method, the application of methodology and the static rating, they can also ensure that almost for 100% of the time they get extra capacity. This is an example of Germany. Germany is having a different approach to the possibilities of the line rating of the lines. What they are doing is to implement in the power flow analysis the methodology in terms of the thermodynamic behavior of those lines. So they upfront calculate their power flow capability, including the thermodynamic effect of the dynamic thermodynamic effect of those lines. And by doing so, they upfront calculate their contingencies, having this into account. Another perspective comes from France. And in France, they introduced the concept of a quasi-dynamic thermal rating, and they apply it not only for lines, but for transformers and even underground cables. Their objective is slightly different from the others because it's to be used on the planning stage and assessing the maximum rating capabilities of the lines, given the known climates in the region, including an accepted risk tolerance for the operator of those lines. I'm getting to the end, and this is a calculation that was made by our colleagues from ENL in the United States. And what they have compared is the cost estimated profit, let's call it this way, when applying different grease-enhanced technologies. And if you could read well, and I am aware we cannot read it very well, in the green, what you have is the application of dynamic line rating, and one recovers the cost when compared with the value for this specific case of curtailed wind energy. We would recover the investment value in applying dynamic line rating in a period that ranges from 0 to 2 years. And from all the technologies that would increase the capacity of the line, this is the most effective one economically. So in short, when we apply and conduct a review of the line rating methodologies, both in use and in Europe and the United States, what we conclude is there's absolutely no doubt that the application of these dynamic line ratings can postpone or even completely avoid the construction of new transmission lines. We could also conclude that nevertheless, those evidences, the majority of the TSOs still opt by applying static or quasi-static methodologies, even if the investments in the dynamic line rating are not very pronounced. One of the things that we concluded in more than one country, and that is something that tends to be a bit worrisome, is using the static ratings. We conclude that for certain weather conditions, the lines are operating above the thermodynamic limits. So they are being degraded by being operated in those conditions. And one conclusion that we could extract from this overview of the last 25 countries is dynamic rating is really a grid-enhanced technique that is cost-efficient and is a tool that can be implemented in this energy transition phase to minimize investment costs and also to use in the most cost-effective way the assets that are already in operation. And I finish with this. Thank you very much.
Thank you, Anna. And now we could actually invite all the speakers here to the front, to the chairs. So we have heard 4 interesting presentations about offshore wind integration and enhanced grid utilization, and now it's time for discussion. So are there questions to the speakers already from the audience? Perhaps we can start with some general questions to all of you. So what do you see as the main barriers for integrating more offshore wind or utilizing these dynamic line rating and similar strategies?
I have the mic, but does anyone want it?
I guess from my perspective, I'm an engineer by training, and I think that we're very good at solving engineering problems. I think we're very good at building technology solutions to things. I think we struggle with frameworks around bringing stakeholders to the table, bringing the right stakeholders to the table, getting the right views, and balancing all of the different objective or all the different competing priorities. So in my mind, that's the biggest challenge or the biggest hurdle that we face. It's not how we get the engineering right, it's how we get the solutions right, how we take everyone's interest into account, and how we move that forward.
I would say this offshore question, it's a lot about permits, of course, but now we also, since we have the shopping list, it's very obvious that the supply chain is an issue. It's not enough in Europe, and it's also these ships, installing ships. There are only 8 ships, to my knowledge, worldwide, and then there's also worldwide business. So it would be interesting for Europe that they work in Europe, but in the wintertime, they tend to work somewhere else. So this is an issue. And then the discussion, should we have bigger wind turbines or not? There are many limitations, and trend is let's keep it in 15 to 18 gigawatt and not increase. Otherwise, the supply chain for these vessels and everything else would also increase. Yeah, dynamic line rating, I think we use it already. And it's I'm in the planning section of our company and of the international planning, and there it's not so much a thing to be considered because it's only short-term buying time. But in the planning divisions, we have longer-term perspectives, and this is a device surviving in the short term, but not really for the long term, because yeah, no, but also production is increasing. Big loads are coming. Also, the needs for system are exploding so much that this is really. We have the impression it's more a drop on a hot stone. Of course, needed and should be used, but it's not the only solution.
It's not the only solution, but it's, as Anna was saying, it's a relatively cheap solution. Part of the problem with the grid enhancing technologies is that there are a lot of different options. So in my slide, I wasn't saying this is the option, please choose it. It's here's all of these different options, and then that raises questions as to why should I choose option A over option B, and when does this one work best, and when does that one work best? But I would say that's a nice problem. It's much better being in a situation where we do have options to choose from, rather than the situation where we're sitting there saying there's nothing we can do. So I would say it's a good problem. And I mean, there are various countries that have implemented these technologies, and I guess they need to spread the gospel of what they have achieved and that it does work and it does make things easier.
Well, of course, I'm going to say that we should use, but one of the things that I wanted to highlight is there are 2 perspectives of using dynamic line rating. One is the operational. We have the lines and somehow we want to enlarge the capacity of the lines, at least for a certain percentage of the time. So we have the asset already constructed. And the other perspective that Angie was saying, that she's in the planning department, and in principle, we do not advocate to use dynamic line rating in the planning and of new transmission lines, with a single exception. If we are planning N10 transmission lines that serve wind power plants, we can rely on the effect, the cooling effect of the wind in order to increase the capacity of the line. Because when the line will be more charged due to the production of the wind power plant, the same line will be more cooled by the effect of the wind. So that's the single exception, not applicable to offshore because the cables are underwater, but for overhead lines, we could and should, I would say, take it into account in the planning phase.
Any questions from the audience at the moment? Yeah. And please say your name and affiliation.
Juha Kiviluoma, hailing from the same place as Nina, VTT Finland. I'm very impressed still with the work that ENTSO-E does and how it has been put together to kind of coordinate a lot of the planning and of course also operations. But I just have the feeling that it makes it so much easier to do planning across countries and provinces or states, wherever you are. And of course, it's not a easy thing to get something like that going on in the North America. But I'm kind of trying to formulate this into a question, but how would you, if you agree on that, how would you try to go about that, and maybe in a bit more accelerated way than the European process has taken, I don't know, 50 years, starting from the Nordic system and the central systems and so forth.
Yeah, I think unbundling was done in the 90s, if I remember correctly, 93 or something. And this is the basis. I learned this week and also last week in the IESVic workshop that this mixture of different governance in the ISOs and RTOs makes it difficult to plan across countries. And I think Madeleine, she said it all this morning. And so I would recommend listen to Madeleine and what she finds out, because I'm also looking forward to when she's ready in, what did you say, around January, maybe, that you will have maybe some recipes for all of us, so even Europe can learn. Also, I have the impression, I'm happy that I'm working in Europe and seen from outside, it seems to be good. But of course, when you're inside, you see all the issues that we still have to solve. So it's not ready, it's not easy. But what is missing here is a bit unified system on which you can build. So this unbundling, so either transmission or generation or trade as separated, makes everything easy, because then you can have for each of the three sectors, you can have rules what to do, and then you can collaborate. And here I noticed that you have these vertically integrated utilities, and I was a bit shocked to hear from Damien that you consider this again, but it's a good thing to compare to maybe to evaluate then what you have. But I think this is a bit missing here, and whoever is able to do anything about that, I think this would provoke a big leap forward, because the rules are coming already. Also in United States and Canada, looking at what Europe is doing, but the basics are missing, my impression. I don't know who is responsible for some unbundling of some utilities here. Maybe Madeleine knows?
Stuart, would you like to add?
Yeah, I might add something quick. No, that's fine. I'm gonna stand over here because I'm right next to the speaker. Sorry. So what I was gonna say is that I think there is this holy grail of federal backstop that's often talked about in Canada, and Brent talked about it earlier today, but specifically, getting eminent domain or having a single organization that can overlook the net benefit or the cost benefit analysis across jurisdictions and make kind of an overall decision around, is this in the public interest or not? Is this project in the public interest or not? And if the answer is yes, then it goes ahead. The reality in US and Canada is that a lot of the energy policy is still held at the state or provincial level. And I don't think you're ever going to see, especially across many states, the individual utility commissions or regulators interested in giving up their ability to permit at the local level or define what's best, from a cost benefit perspective. And we don't have a federal carbon or decarbonization plan in the US. And I would say in Canada, it's a bit of a patchwork. And so we're not going to get this kind of central planning piece of it. That being said, we don't want to give up. There's a lot of opportunity, I think, for aligning different systems or aligning different regulators and what they're doing, even just from a timing approach to make it easier for either merchant generators or for others to bring different opportunities to the market. So if you look at the proceedings as an example, or the transmission planning processes for different regions, they don't align. They're different timelines. They have evidentiary processes at different times. They look at net benefits in different ways. Even just aligning the evidentiary record of those or the timing of those so that everyone's looking at kind of load planning at the same time, and then everyone's looking at resource options at the same time, and then transmission options at the same time is extremely helpful. Because right now you can enter one process, 18 months down the road, you have to enter a second process, your project changes. There's no streamlined way, not that there's anything streamlined in transmission development, but there's no streamlined way to participate in multiple jurisdictions planning processes at once.
Thank you.
Maybe just to comment further that, I mean, in Europe is different countries and they really disagree on many things, but I think the value of the NSOE and also Acer is in a degree that they have removed a lot of politics out of it, and maybe just by kind of I mean, nowadays they do planning together, but that wasn't always the case, and I think it's just a very good thing to get these people in the same table in regular fashion and start talking, and maybe eventually they'll lead to something.
I completely agree. And I think, there was a lot of hope when FERC Order 1000 came out, and there was kind of some level of interregional transmission planning put out there and a guide. I don't think it's gone far enough, but I think we're absolutely with you. Getting at the same table and having those conversations and trying to move some of those forwards is pretty critical.
Thanks. Maybe we can also continue with the other speakers. So how do you see, based on your experience and the studies that you have presented today, are there some specific practices that you would recommend to increase interregional transmission, or some practices that you would not recommend?
Well, I already have the microphone, so I'll start. I think I would reinforce what you said, and thinking that you said the provinces in Canada do not want to drop their capacity to permit and being self-sufficient in their governing, let's call it. And you announced the fact that we had a similar situation in Europe. No, we had a much worse situation because they are nations, they are not provinces. And I would say these days that nobody in Europe thinks that they lost that. So they gain in terms of the capacity to transmission, in more efficient costs, in the capability to share reserves, to count on your neighbor in emergency situations and all those benefits in terms of grid operation, not to talk about the costs that tend to be balanced among countries. So we feel that we gain lots of things, and I never experienced any country or any situation in which the individual countries in Europe think that they have lost the capability of permitting, of deciding by themselves. So maybe that is somehow inspiring for you.
Everybody has probably said what needs to be said, but I think the interesting thing about Europe is that it isn't a single power system. You have the Irish power system, you've got the British power system, you've got the Nordic power system, continental Europe. And so they are separate systems, but they do work together with common aims. I suppose the other aspects as well is that you talked about different flow processes and different timing processes. And in Europe, they try to establish common codes so that if you are a developer, rather than, developing your wind turbine technology that follows all the rules in one country, and then you switch to a different country and you have to have different rules and different standards, that, there are attempts to try and standardize that across Europe so that things can easily, you're not reinventing the wheel each time you move to a different country. And that benefits everybody because costs are lowered.
Thank you. Yep.
Several synchronous areas, not systems. It's one big system from Finland to Portugal.
Hi, Peter Fairley again. Is it Antje?
Yep.
Hi. You mentioned the slides you showed, and you talked about how from your offshore development plan, most of the new lines would be radial. And also that, well, I was curious on that point, whether the supply chain issues come into play there, and is there a possibility that if there's a really high costs and limited availability to those lines, does that change that finding? And then also I was hoping you could explain why the availability of DC breakers changes the picture so much on the hybrid side.
First, the last question, also the DC breaker facilitate flows between market zones. It's a bit more expensive per line, but you get a completely different system. And when you have zones across different market zones, then again, prices equalize, and the system cost, the social cost for the socio-economic welfare for European community has benefits, and this compensates for the costs we have to spend. And so also we have benefits in security of supply, because when something fails, there's more paths where electricity can be exchanged between ourselves, and we don't have to curtail, but there's a different path for the energy to flow. I forgot your first question.
Well, before I restate it, can you just say does that anticipate a meshed DC grid that's operating both onshore and offshore?
No, it's in this study, because it was had to be done very fast. We only looked at the offshore system. Also, we used the pan-European model, but only optimized the offshore sea basins. We did not optimize the onshore system as well. But we can, and as offshore distances are long, we had to use HVDC. We decided to use the de facto standard, which seems to evolve 525 kilovolt and 2 gigawatt. And then, I'm tired, I'm sorry. Yeah, it's now 1 o'clock in the morning. Help me, please.
The first question Now that you've answered that one, the first question had to do with radial versus hybrid connections, and when you factor in the supply chain issues with HVDC, does that change the ratio of
No.
radial to hybrid?
No, it's a lot anyway on cable. I know that one of the TSO colleague companies, they reserved the supply chain for the next 8 years. So it's good then to buy that standard. Otherwise, the supplier puts you further at the end. So supply chains is an issue no matter what. And also the radials are very often so far out of the shore that this could also be HVDC. So the countries starting, they usually use closer to the coast, which could be up to, let's say, 50 kilometers AC, because onshore you also need a piece of land. So then you have these 80 kilometers. And then, yeah, supply chain is an issue no matter what. And what we reached with having DC breakers is we have an increased interconnection level of half the amount that we found for the entire European system in the T1EP 22 for on and offshore. So it was just a few spots. So you remember it was only the lighter green part in this bar charts, not very impressive. So it's not good for political messages, but it makes a huge difference in how the system is used. And that is then the big advantage. Also only a few spots needed in the waters make a big difference. And so the investment seems to pay off. But let's see what are the new targets facing the speed we need and facing the supply chain issues. And yeah, I'm really curious what the member states deliver now and for the next round. So changing political messages is also not so easy from within 2 years, but facing these questions, they try to solve supply chain issues, they try to help with the vessels. There are methodologies how to share the cost since 2013 actually, but seems not to work also on sea basin level. So this was designed for single projects, but sea basin is a different discussion.
Thank you. Is there still one quick question? I think we could have time if there is one. If not, I think we can end the session already. 3 minutes late, but not bad. So thank you for your attention. Thank you for the questions. And once again, thank you all the speakers.